Since the late 20th century, we have depended on plastic as an affordable, versatile and durable material. However, since the majority of plastic materials take centuries to degrade, all of the plastic that has been sent to landfill. Assalamualaikum to all dedicated lecturers and examiner. My name is Nur Masyitah Hazirah binti and my supervisor is Professor Madya, Dr. Hajar Famiza Abdul Latif. My final year project is alternative fuel from polystyrene. Background study. Did you know that according to Kumar et al. 2021, the grew of plastics manufacturing increased 4% from 2012 to 2013, which this led in a rise of disposable rubbish at landfill. Besides, according to Pandey et al. 2020, pyrolysis is a thermal degradation of long-chain organic molecules into smaller hydrocarbon. Furthermore, pyrolysis of plastics was conducted to recover plastic waste, as polystyrene is a petroleum-based product. Next, the problem statement is the demand of plastics have contributed the increasing waste in landfill. Next, because of the open burning activities at landfill is said to reduce the amount of waste and results in air pollution. Next, significance of study is to reduce the amount of plastic waste to be disposed at the landfill, as well as to reduce the emissions of toxic gases from the burning of plastic waste. Next, to gain liquid oil or alternative fuel from polystyrene through pyrolysis process. Moreover, the objective is to convert polystyrene into fuel and to determine the properties of fuel obtained from polystyrene waste. Before we move to the methodology part, let's take an overview of reactor use. The reactor use was the Evolved Gas Analyzer (EGA). The reactor was equipped with the condenser tube as well as collector tube for oil and gas, cell temperature to indicate the inner temperature of the reactor, heating panel, tube for nitrogen gas, and the ice box which placed under the reactor. Next, methodology. 3 samples was prepared for each temperature and was weighed 2.5 gram, and after that, the temperature was set at 400 degrees with 1 ppm per minute of nitrogen gas. The process was repeated for 425 degrees. During the process, the gas was collected in Tetla gas bag and was analyzed with gas chromatography thermal conductivity detector (GC-TCD). At cooling temperature, char was collected at the end of process and was analyzed with flame transform infrared (FTIR). Furthermore, results and discussion. Product from pyrolysis collected was char and gas only. Thermogravimetric analysis (TGA) was conducted before pyrolysis to measure optimum temperature. The results show polystyrene was decomposed at lower temperature, which is at 200 to 230 degrees, and it starts to completely decompose at 270 to 400 degrees. Next, the gas analyzed in GC-TCD result in carbon 6 plus, oxygen and nitrogen gas. The oxygen gas should be lower or supposed not to be happen because pyrolysis is process where the absence of oxygen. The nitrogen gas is expected to happen because the use of nitrogen gas was at early at the process until the end. However, other gases, for example carbon dioxide, absence because the temperature used was too high, which is 400 and 425, as the polystyrene was completely decomposed at that moment. Moreover, as temperature was set 400 and 425 degrees Celsius, the char was produced. Therefore, FTIR was conducted to measure chemical compound in the polystyrene after pyrolysis process. The results showed the char consists of aromatics, alkenes and alkenes functional groups. The peaks are recorded in table below. The peak observed at around 1000 to 1600 cm-1 was the aromatic carbon-hydrogen bond stretching mode. This peak is often referred to as the aromatic ring peak, and it is a characteristic features of polystyrene and other aromatic compounds. Other peaks also observed, such as the alkenes group at 2917.4 cm-1 and alkenes at 3024.4 cm-1. In conclusion, the converting polystyrene was into alternative fuel can be determined through the pyrolysis process. However, it is crucial to know the optimum temperature used in this experiment. Besides, the properties or characteristics of polystyrene waste after pyrolysis can be observed by using its char and gas production in GC-TCD and FTIR. There are a few limitations in my final year project where the liquid oil or fuel is not able to produce because the temperature chosen was too high. The best temperature for pyrolysis of polystyrene is actually depends on the desired product. At lower temperatures, which is below 400, the pyrolysis process is slower, leading to a higher yield of liquid products. However, the liquid products tend to be of lower quality and require further processing to be useful. Meanwhile, at higher temperatures, the pyrolysis process is faster, leading to a higher yield of gas and char product. That's why in this experiment, I couldn't get the liquid product as temperature chosen was too high, which is 400 degree and 425 degree. However, if the goal is to produce a solid char, a temperature range of 500 to 600 degree is preferred. On the other hand, if the char produced at higher temperatures, it tends to be more porous and less dense, which can reduce its usefulness for certain applications. Furthermore, the presence of oxygen is because the small amount of oxidation occurs during the setup, which is before the nitrogen was supplied. For recommendation, we can use catalysts in order to enhance the liquid oil production, which have been proved by a study conducted by Miandad R et al. 2019, where the catalytic pyrolysis of polystyrene produced a higher liquid oil for about 60 to 70% by using TANZ and AANZ catalysts. Besides, we can use vacuum or inert atmosphere during pyrolysis to minimize the degradations of the product as well as improving its product quality. Thank you. That's all from me. Assalamualaikum warahmatullahi wabarakatuh.